call that up real quick. You guys had an average of 600, no, not 603, that's too big. I emailed it to myself, hang on. I emailed it to myself because I was checking it on Monday evening. So let me go back to Monday. So there we go, 309. That was your guys' average, 309. That's what you came up with on your steps. The actual number, I don't remember, but it's okay because I created a spreadsheet to aid me with it. And this is kind of giving you a hint at where we're headed in the back half of the course. Estimation, coupon collector. This is actually a bit of a derivation of an old question called the coupon collector problem, which if you have a certain number of distinct coupons that are in like a box of cereal, I think that's where it all started. Boxes of cereal, some have little prizes or something, and coupons that you can redeem for things. And suppose there's 6 different coupons. How many boxes will you have to buy on average till you get each one? Well, that's the same thing as rolling dice, assuming that they're randomly spread throughout there. The mathematics of it's actually very, very interesting. What you have to do is you have to add up what's called an infinite harmonic series. What? So if you, exactly, what? So if you have a die with 6 faces on it, remember how we did that in class? We rolled a bunch of dice and then we averaged your results. And we ended up getting something like 13 or something, 14 on average. Well, it ends up being, 14.7 is the average for that. And the way you do it mathematically, and we'll play with this more as this class goes on, is you do 6 over 6 plus 6 over 5 plus 6 over 4 plus 6 over 3 plus 6 over 2 plus 6 over 1. You add all that up, and what that adds up to is the average that you guys came up with experimentally. Now, why you add all that up is what we need to work on over the next 5 weeks. Because it's called the expected number of rolls to get a certain number. So for example, when you throw the die the first time, anything you want, the first number comes up. So you only have to roll it expected 1 time to get a number that you need. Does that make sense? So you roll a die, you get whatever number you get. Now, you also need to get another number after you get that one, correct? After you get that one. The probability of getting the same number you just got is 1 in 6. The probability of not getting that number is 5 in 6. That's the probability you have to hit to get a different number. And the average number of times it takes is the reciprocal 6/5, which was the 6 over 5 we just mentioned. Then you have 2 numbers out. The average number of getting the next number would be 6/4, which was the next number, and then 6/3, 6/2, 6/1. So, for your guys' problem with the Star Wars problem, you had 66 cards, I believe. Here you are down here. There you are right there. You, on average, have to do 66 over 66 plus 66 over 65 plus 66 over 64 plus 66 over... And Shelly's going, stop! And that's why God invented Excel. There's the true average number of cards you have to buy. 315. How did you guys do with your average?
Damn good.
Pretty damn good with 309. You see what I'm getting at here? Who understands this fully? Nobody in the room except me. And that's only because I studied this and I love this and I think it's beautiful. But that doesn't change the fact that we can spend an entire time in Math 105 learning just this and you still might not come up with an understanding of it. But I think everybody gets the idea of running that estimation program and counting up and averaging the results. So what we've done is we've brought some pretty crazy mathematics really, really close. And watch this. I did a little extra math for us. Check this out. This is kind of crazy. Here are the first 20. First 20 dots in the pattern. What you're looking at here is this down here would be the number of distinct sides on your die, quote unquote. So 1 side on a die, 2 sides on a die, 3 sides on a die, 4. And you're saying, what dice have 6 sides? Sure. Yes, I know. But a coin is only a 2-sided die, isn't it? Right? If you think about it. And buying the Star Wars cards is a 66-sided die, isn't it? Does that make sense? So what I did was, I put a pattern, a scatter plot, if you will, thank you, a scatter plot that shows the number of sides on the die and the average number of times you have to roll it to get them all. Look at that graph. I wasn't expecting this at all.
Linear.
Looks damn linear, doesn't it? Looks damn linear. So what I did then, threw a trend line on there, a linear trend line. We're going to make it linear. We're going to put the equation on there too. Here he is. Hot damn. Let's make it bigger so you can see it. Oh, look, it's Arial. We'll leave that font. That's a good one. 3.812 x minus 7. How's the fit? Damn good. I mean, it underestimates over here. See how the points are above? And then it begins to overestimate, and then it looks like it switches back to underestimation. It's not a perfect line, but in the first 20, it's not bad. So it's the best fit over the first 20. We can probably find a better fit, which we'll play with today. That's part of what we're going with today, is looking for a better fit in a line sometimes. So how many would it estimate we would need with 66? Just plug 66 into that, right? So I'm going to call that 4, because I'm Sean, and I do estimation. 4 times 66 is 240 plus 24. 272 minus 7 is 260 something. That's actually under quite a bit, isn't it? That's actually under quite a bit. Why? Because my math is bad? Well, you guys are using fewer more precision. Yes, Aaron, what would you get right there?
257.
257. Close enough to my crappy estimate up here. 257, which I think is pretty low compared to what it should be, right? It should be at 315. I'm down by 60, which is kind of inexcusable, actually. Why? What did I just do? What's that word called that I just did? Micah?
Estimated.
I did estimate, but I estimated on a model with which I was extrapolating. So I was assuming the behavior of these points was going to continue past, because it's not the 20, remember. I took it out to 66. That's an extrapolation. And we know sometimes extrapolations don't work. So what I'll do is, let's make this a little bit smaller so you can see it. Let's pop the data out. Select the data. It stops there. Maybe I have to make the actual... Oh no, let's select more. Let's make it go down... Wait a minute, hang on. What's this data coming from? Oh, here we go. I have a pattern more. There's 20 more. Huh. I guess I never made it do. I want to go into the pattern more. There we go. That's what I want. There it is. Now that's a hell of a lot of dots. It's really hard to see because they're crunched up together. But it is kind of hard to see because they're crunched up together. But there is a belly in that. It is not linear. It's more of a bellied curve, and you can kind of see it with 20. With 20, it was even obvious with 20 more than just all of them. Let me back it out here. See that belly right there? So you've got an issue in that there appears to be a pattern in this data that might not be linear. I'm not saying linear didn't fit it very well. It fitted okay for 0 to 20, but when you try to go past 20, something else happens. And that's what we'll get into today after the break, is why we might need other patterns besides linear. Linear is great, but it also falls short with certain applications. Cool? Take 5. We'll come back.